Hello, today I'm going to present my work, Capacity Cryptographically Enforced in-process capabilities for modern ARM architectures. The work was accepted in ACM CCS 23. It got awarded Distinguished Paper Award. I am the main author, Dinh Duy Kha. First, let's talk about our lab. Our lab is System Security Labs, sslab. Advisor is Professor Hojoon Lee. I am Dinh Duy Kha, a fifth-year combined student. My research area is trusted computing, software security, and operating system security. First, let's start with the motivation for the work. Today's programs are often complex, yet monolithic. What do I mean by monolithic? Everything is combined into one. A program often employs third-party libraries that might contain bugs. Moreover, low-security components, like libraries, share the same address space with higher security components, such as the one that access the private key. And for this reason, a single vulnerability anywhere within program can affect the entire program. So what can go wrong with this kind of monolithic program design? A prime example you probably remember is the Heartbleed incident that almost broke the internet by leaking the web server private key through a buffer overread vulnerability in a TOS extension called the Heartbleed. This vulnerability exemplifies the lack of isolation in modern programs and call for the need of isolation. Most vulnerabilities came from bugs. But as research showed, fixing bugs before they happen is challenging or would incur significant cost. Instead, another approach is to apply the principle of least privilege. With this principle, you may isolate sensitive data and code from untrusted components. On the other hand, you may compartmentalize a program into smaller components such that they interact with each other through limited interfaces. A real-world example of this is the modern web browsers such as Chrome or Safari. They employ a process-based architecture where each smaller component is split into a dedicated process. However, there are certain limitations in splitting complex programs into processes. They require high engineering efforts since it has to be incorporated from the design of software itself. This approach also incurs high overheads from inter-process communication and context switching. To tackle this limitation, researchers have been exploring in-process isolation. They bring the isolation boundary into within the process. They utilize in-process isolation boundary such as function calls so that the program don't have to be significantly modified. Moreover, isolation is enforced within the same address space, so there are lower context switching and communication costs. Recent works employ hardware isolation. For example, on Intel x86, there's the PKU feature that enforces domain memory isolation for memory pages. On ARM, there was a feature called memory domains. However, it's only available in ARM 32 bits and was removed for ARM 64 bits. The need for process reference monitor came from the fact that kernel is unaware of in-process isolation scheme, leading to pitfalls. For example, some process may abuse system calls such as mmap and mprotect to overcome the page-based isolation, for example, used in Intel PKU. For this reason, there has been works that introduce in-process isolation-aware process reference monitor. They limit the powerful system calls such as mprotect, and also filter system call arguments such as open according to their resource ownership. Now let's go over capability-based access control, one of the main security principles behind capacity. Capability-based access control gives subjects capabilities or capability tokens to access to certain protected resources. Capability tokens are authenticated right before granting access to the resource. There has been work that incorporate the capability model into system security. For example, pointer as capability tokens is explored in Cherry. For OS access control, there are previous works such as CASCM or SEL4 microkernel that bring the capability model into OS. Now, let's go over the hardware features that are available in modern ARM architectures. Two of them are pointer authentication and memory tagging extension. Those two features are used for memory safety. First, let's talk about pointer authentication. Pointer authentication introduces PAG instructions to compute pointer authentication code, or simply PAG. PAG is attached to the unused bit of a pointer and can be authenticated using the AUT class of instruction. You can think of it as similar to MAC in TLS. However, the untrusted medium is the memory that can be corrupted instead of the connection. To compute and authenticate PAG, one of the 5 kernel managed key IA, IB, DA, DB, and G, along with a 64-bit modifier, may be used. Next, MTE, memory tagging extension. MTE implements tag virtual address and memory. It uses a key and lock mechanism. Memory access is only allowed when the pointer tag matches the hidden memory tag for each 16 bytes of memory. Pointer authentication and memory tagging can be enabled at the same time. And when that happens, PAG and MT are located on different bits of a pointer, as you can see on the figure. One key observation we see is that those two features has characteristics of a capability-based access control scheme, where a sign and tag pointer become a capability token. Based on this observation, we built an in-process compartmentalization framework called Capacity. At the core of Capacity are modern ARM PA and MT hardware features. It provides a lifecycle-based protection of sensitive resources inspired by capability access control. Here is an overview of Capacity. Capacity divides the applications into domains, where each domain has exclusive access to their sensitive resource. What is a domain? A domain are subgraphs of execution wrought between inline domain switch, called capa enter and capa exit. The remaining of the process does not belong to any domains, are called the ambient domain. Capacity identifies each domain with a unique pointer authentication key called the domain authentication key. And upon entering a domain, Capacity switches the kernel managed PA key to the domain authentication key. In the ambient domain, the ambient key is used instead. For each of the domain, Capacity provides life cycle protection for the references of the resources. Considering a common case of secret import and use, the file path, for example, a circuit key, is first passed to the open system call to obtain the file descriptor, for example, a number 5. The file descriptor is then used to load the content of the file from the file system into memory, for instance, the read system call. The secret key content is then accessed through pointers. Based on this use model, we saw that Capacity must provide lifecycle protection of the resource use. Capacity provides lifecycle protection of resources with its internal reference monitor for the file system reference and the instrumentation plus the heap allocator for user space reference. Together, they provide complete mediation of resource creation and use. Capacity transforms kernel space and user space resource references into cryptographically non-forgeable references. The construction of those references are accelerated through pointer authentication. We introduce a in-kernel reference monitor to perform domain authentication and key switching. It also enforces access control on file-related resources, such as the file path and file descriptor. Especially, it makes sure file descriptor references that are given to the user space through system call and those that are passed to the kernel in system calls are signed and authenticated. Our instrumentation framework and runtime allocator ensure that all user space pointers are tagged and signed using PA and MTE. For the stack memory, we introduce an instrumentation framework to tag the function stack frame, and also we introduce a memory allocator that returns tag memory and pointer. On those tag pointers, we perform whole program instrumentation that sign pointers before they are stored into memory and authenticates them when they are loaded from memory into a register. We have just now covered the overview of capacity. Let us now visit two of the capacity core concepts, domains and references. First, capacity domains. Aside from the authentication key, each capacity domain also associated with a dedicated empty tag. The ambient domain is given the ambient key and the tag of 0. We use the key DB for the domain authentication key since it is unused by most pointer authentication-based defense. The DA key is used for the ambient domain. Capacity components turn process references into non-forgeable cryptographically references. The two forms of capacity references are the signed file descriptors and the pointers. Capacity then split program references into domain private references and ambient references. The domain private references are exclusive to their owner. On the other hand, the ambient references are accessible by any domains. Domain private references are signed and authenticated before they are used with the domain authentication key, the key DB. We authenticate and sign reference before they are used with the domain authentication key. And with this, they can only be successfully authenticated when the context is within the owner domain. When another key is inactive, or when the ambient key is used, authentication would fail. On the other hand, the ambient key is used for ambient references. This key remains the same throughout the execution of the process, so all domains can access these references. To demonstrate capacity workflow and functionalities, we use a simple example. In this example, the sensitive resource to protect is the secret key that is loaded into memory and used by the two functions, load secret and encrypt. So ideally, we want to put the use of the secret key and the in-memory buffer that contains the content in a dedicated domain. First, domain switch into the domain is inserted to establish the domain boundary. On receiving the request for entering the domain, our reference monitor will switch the active domain authentication key to that of the target domain and switch back upon exiting the domain. Take the load secret function that is executed inside the domain crypto, for example. Our reference monitor will authenticate the file path and return a file descriptor that is signed with the domain authentication key. For user-space references, the programmer needs to annotate the sensitive resources that should be authenticated with the domain authentication key. And for file-related resources, such as file system paths, you may assign the file path to the owner domain during program initialization. The compiler annotations guide our instrumentation framework. Dump-pref mark the sensitive pointer so that they are 10 track, and dump-pref-func instruct our compiler to tag the function stack frame with the domain tag. Our pointer authentication instrumentation is aware of domain private references. The instrumentation first starts with programmer annotation on the sensitive pointer. Based on the annotation, capacity performs tent analysis to find the propagation of such pointer and perform selective instrumentation, where domain private pointers are signed and authenticated with PACDB, in other words, the domain authentication key. For the remaining ambient pointers, we use PACDA and AUTDA, which is the ambient key. Finally, the programmer may annotate cross-domain interactions. In this example shown in this slide, there's no such cross-domain interaction. But imagine, for instance, load secret and encrypt are to be placed into separated domains. Then there need to be delegation of reference from one domain to another. For the evaluation of capacity, we perform micro-benchmarks on runtime library, the reference monitor, and the instrumented code. We ported 3 real-world programs to use capacity and use capacity to enforce fine-grained domain-based isolation. All experiments are conducted on a M1 Mac Mini using the ACM Linux, where pointer authentication is supported natively. Since there's no MTE hardware at the moment, we rely on QEMU for functional correctness and emulate the overhead. Here is an example of capacity in practice. We use capacity to isolate the web server private key and the session key. We introduced 2 domains. One has exclusive access to the private key during TOS handshake. When a session key is generated, it is then delegated to another domain for handling the session. In Nginx, we also include other domains for finer grained isolation, which you can learn more in the paper. Here are the results of the web server benchmark. We measure the throughput for baseline, which is the unmodified Nginx web server, and the capacity-enabled Nginx. Overall, capacity overhead is 17% for single-threaded and 13.54% for multi-threaded on different file sizes. In summary, we introduced capacity, a capability-based in-process compartmentalization framework. It utilizes ARM hardware acceleration for efficient capability-based resource isolation. It provides a coherent lifecycle protection of sensitive resources. The evaluation shows feasibility in real-world applications. For more details on the design and implementation and a more thorough security analysis, you can find them in the paper. That's it for the presentation. Thank you for listening.